Lake ecosystem models are increasingly applied in research and management of lakes worldwide. Many lake model studies include scenario simulations that explore how best to combat impacts of, for example, global climate change or eutrophication. My name is Tobias Kuhlmann Andersen, and I'm a PhD student at Aarhus University with funding from the Sino-Danish Center. In the next 15 minutes or so, I'll show you how a Danish research project levied 20 years of comprehensive monitoring of shallow lakes to explore and illustrate the use of lake ecosystem modeling in management and policy. Many brilliant people have contributed to the work presented in this talk. I want to acknowledge Anders Nielsen, Nicolas Asana Schneldermeyer, Fen Huan Hu, and Dennis Trolle. This project was funded by, among others, the Danish EPA. To explore the benefits and challenges of lake ecosystem models in a Danish lake management perspective, 5 lake models were set up, calibrated, and validated for 5 different Danish lakes. In this presentation, I'll show you simulations from 3 of them: Lake Hinge, Lake Ravn, and Lake Brørup. First, I'll zoom in on the shallow Lake Hinge with a watershed dominated by agriculture and see if we can show you how the lake model reproduced observed lake dynamics. I will also show you how external load scenarios can be applied in setting nutrient load thresholds for the lake. Furthermore, I'll demonstrate how the model can evaluate also in-lake restoration methods, such as oxygenation of bottom waters. And lastly, I'll present new model developments. But first, let's have a look at the lake model we use. The Water Ecosystems tool, or just in short, the WET model, is a dynamic process-based model. WET simulates a mass balance of phosphor and nitrogen in the water column and the sediment. In this study, WET was coupled to the hydrodynamic model, the general ocean turbulence model, that allowed simulating a one-dimensional water column, as represented by this figure in the lower left corner. Each water layer includes a sediment, which is very useful if you want to simulate depth-dependent processes, for example as sediment nutrient release or macrophyte establishment. In each water layer, you'll find the most important pools in a lake ecosystem. For example, organic and inorganic nutrients, several groups of phyto and zooplankton, as well as macrophyte, zoobenthers, and fish. All organism groups are modularized, so the user can decide how many functional groups to include in the model. WET also simulates oxygen dynamics and dry rate for all organisms. All these pools are, of course, interconnected through various processes, for example, grazing, settling, or mineralization. Now, let's have a look at one of the 5 lake model case studies. Lake Hinge, as you can see here, is a shallow lake with a mean depth of 1.2 meters and a short retention time between 2 to 4 weeks, depending on the season. If we take a look at the catchment of Lake Hinge, we clearly see the Lake Hinge is located in an agricultural landscape. All the yellow on the catchment map is agriculture. The lake has experienced decrease in the external nutrient load from the early 90s, most likely caused by a decrease in the amount of fertilization used on the surrounding agricultural areas. Lake Hinge has been included in the Danish monitoring program also since the early 90s, with most of the catchment being monitored, as you can see from the shaded area on the catchment map, as well as also physical, chemical, and ecological parameters in the lake. So let's see how the model reproduced all these observed lake dynamics for Lake Hinge. Let's first have a look at the observed temperature and dissolved oxygen concentrations. The dataset has been split into 7 years for calibration from 1993 to 2000 and 7 years of validation from 2000 to 2007, with the circles marking the observations and the black line being the model simulations. The lake model, as we can see, reproduces both seasonal timings as well as magnitude for both the calibration and the validation periods, although the model is a bit more challenged in reproducing the high variability of the dissolved oxygen concentrations. We can also look at chemical water quality parameters. Here we see model simulations for total phosphorus, total nitrogen, and chlorophyll A concentrations. The shaded area or the shaded band around the observations illustrate the measurement errors. The wet model is clearly able to reproduce both seasonal and interannual patterns of nutrients in Lake Hinge across the 14-year period. For the chlorophyll A concentrations, in most years, the model reproduces both the magnitude and timing of spring and summer blooms, as well as a clear water period in between them, as we can see for the year of 95. The model performance for Lake Hinge is very similar to the model performances for the other Danish lakes. Currently, in the Danish So here, to look at the other lake performances, we compare model performance for the Danish lakes against model standards applied in the marine management in Denmark. All model performance for temperature, total nitrogen, total phosphorus, and chlorophyll A are excellent to good within this framework, and they're also very much comparable, or actually for some parameters better, than other aquatic model studies. But currently, in Danish lake management, empirical relations are applied to set external nutrient load targets for restoration. So how are the dynamic lake model performing against empirical relations? And can the dynamic lake model decrease uncertainty within the lake management? Here, we compare predictions in summer mean chlorophyll A concentrations for the dynamic lake model, that is simulations of the bars in orange, against the observations, that's the red bars, and then against 3 commonly used empirical relations, that's the blue and green bars. The empirical relations are based on relation between prediction of summer mean TB concentrations and summer mean chlorophyll A concentrations that are estimated on a data set of plus 25 years of data from the Danish Lake Monitoring Database. Still, we see the application of the calibrated lake-specific model can more precisely predict the summer mean TP and chlorophyll A concentrations, as we can see here for Lake Hinge. This has been observed for other lakes and empirical relationships as well. This is not surprising. Since the dynamic process-based models that we have adapted here to each specific lake, whereas the empirical models are built on the data from a wide range of different lakes. It should be noted, however, that some of the empirical models may in some cases reflect actual observations extremely well, or even better than dynamic models. So, with a lake model reproducing specific lake dynamics, we are ready to investigate management and restoration strategies for Lake Hinge. Therefore, we simulate 5 different nutrient load reductions from the period 2001 to 2005 for Lake Hinge, with a baseline with no external nutrient load reductions in the lightest blue and an 80% reduction in the darkest blue, as we can see for total phosphorus, total chlorophyll A, submerged vegetation coverage, and the diatom biomass as well. As expected, higher reductions in nutrient loads result in a decreased phosphorus and chlorophyll A concentration, and in contrast, the submerged vegetation benefits from the reduced nutrient loads and increases in coverage. Here we see it's also possible to assess when the lake water quality has improved. We can extract summer mean chlorofluoric concentration from all the scenario simulations with altered external loads to visualize the impacts across external load with a bifurcation plot. This is done here with the external P load on the x-axis and the summer mean chlorofluoric concentration on the y-axis. The green and blue connected circles represent one scenario with altered load initiated with either baseline or clear water condition. With the current baseline load of around 9 milligrams phosphorus per square meter per day, the external P loads are predicted to be reduced to about a third to achieve clear water conditions with high coverage of macrophytes. So, with the lake-specific dynamic model can actually guide our targets for restoration. But these are not the only these are not the only restoration strategies that can be evaluated with the WET model. The lake ecosystem model can also simulate and assess different restoration strategies. Internal, for example, oxygenation of the hypolymium in the summer stratified Lake Ravn, which was also one of the lakes in our project. Here you see two simulations of dissolved oxygen concentrations and phosphorus, one with no oxygenation simulated and one with oxygenation simulated at 22 meters. As we see, the hypolymium phosphor concentrations are high each summer, but in simulations with oxygenation at around 22 meters, the hypolymium oxygen concentrations are increased, which prevents release of phosphor from the sediment. And simulating oxygenation is just one of several new model developments for the WET model. In another of our investigated lakes, Lake Bryrup, cyanobacteria surface blooms are common in late summer, illustrated by this picture here. With WET, it is now possible to simulate surface blooms. In two figures, as you can see to the right, you see daily outputs at midday for Lake Bryrup in 1994, with the simulation beginning in January. In spring, diatoms dominate the phytoplankton community, and when the lake temporarily stratifies in summer, WET simulates cyanobacteria surface blooms. This is due to the cyanobacteria configured with an active ability to swim upward. So we see surface blooms at the surface. And it is not only phytoplankton that now have the ability to swim. We can also simulate diurnal vertical migration with WET for the zooplankton. For 2 days in July in Lake Bryrup, Daphnia migrates to the deeper water layers during the day, and they're then closer to the water surface at night. So with WET, we can also zooplankton can also be configured to avoid low oxygen concentration, so they will move upward if the bottom waters have too low oxygen concentrations. In conclusion, the dynamic process-based water ecosystem tool can provide a powerful tool for lake managers and water authorities in simulating lake ecosystem dynamics. And with the ability to reproduce lake ecosystem dynamics across multiple trophic levels and simulate and investigate external and internal restoration methods, the WET model can serve as one of the tools that can guide the preservation and restoration of our lakes, of our shallow lakes. Thank you for your time in listening to this presentation. For more information on the project and the studies presented in this talk, please go to our website, wet.au.dk. Here you'll also find the slides. Are you interested in started lake modeling? You can find a lot of video tutorials on how to set up, calibrate, and run scenario simulations with WET for your specific lake on this link as well. Have a great day.